Today is our special arranged seminar in celebration of the Heliophysics Big Year. The December theme of the Heliophysics Big Year is citizen science. While we will not have a December seminar because second week is the AGU week, we arranged the November seminar to be the theme for citizen science. And we have gladly invited Pamela Gay, who has a lot of experiences about citizen science projects. So we are very happy and proud to have her as our seminar speaker today. Dr. Pamela Gay is a senior scientist at the Planetary Science Institute and director of CosmoQuest. She leverages technology to collaborate across a broad range of topics across astronomy, from variable stars to galaxy evolution, as well as planetary surface geology. Beyond her researches, Pamela is also dedicating to using new and social media to engage people in learning and doing astronomy. Pamela is well known as co-host of the long-running Astronomy Cast podcast, in which she and Fraser Kane, producer of Universe Today, have produced the weekly cast about astronomy to listeners for 17 years. To get people not only to learn science, but also do science, Pamela has also built the CosmoQuest virtual research facility, which is a citizen science site for the public to participate in NASA-related science programs with access to online seminars, star parties, classes, and more. We are so happy and proud to have Pamela as our speaker today. And today's Zoom, we will not use the screen sharing, but we have spotlight Pamela's video. So for our audience, if you set your own Zoom to speaker view instead of gallery view, you will see the spotlight video from Pamela all the time. So we will work this way. So happy to try some new feature of Zoom that I didn't try before. Okay, so I will give our time to Pamela and hi. Thank you.
Thank you so much for that really good introduction. We are trying many experiments today. I'm also live streaming this out to Twitch on CosmoQuest X. So this is truly going out to the public in a variety of different ways. Now, today I'm going to focus in on citizen science and all the different ways that it has throughout history enabled more and more research to be done and things to be discovered that otherwise we probably wouldn't have understood as soon as we did. And this is based on a presentation that I've been evolving year after year after year. And it's gotten to the point where there is so much citizen science being done that I had to hide roughly half my examples so that I'm not here for 4 hours talking to you. So I'm trying to highlight the best examples throughout history and in our modern day. And you are welcome to ask me all the questions in the world at the end, because there are many things that I had to omit that are possible, and brainstorming is always welcome. All right. So well, let's go ahead and look back in history. So on May 14th, 2009, the first infrared and submillimeter space observatory was launched, and it is named after William Herschel. William Herschel was originally a musician. He was an oboist, a piano player, and also enjoyed the cello. He was a composer of 24 symphonies. And in his spare time, he discovered Uranus, 2 moons of Saturn, Mimas and Enceladus, as well as the 2 moons of Uranus, Titania and Oberon. He studied proper motions, cataloged double stars and nebulae, and is renowned for building some of the first great observatories. In 1872, William left behind his life as a musician and accepted a position with a pay cut, which somehow will make sense to everyone out there watching who is a professional researcher. He took a pay cut to become the royal astronomer. And The way he got engaged in astronomy is a story that even today would sound familiar to a lot of people. In 1873, William Herschel found his passion in the stars because someone walked up to him and said, and I'm looking for a book on my desk. In modern day, you don't have books on your desk. Someone walked up to him at an astronomy meeting and said, I have this book on astronomy. I think you would enjoy it. And then another friend took him observing, showed him things through a telescope, and Herschel got hooked. He started studying the sky and recording everything he saw. And then one day in 1881, he saw a small blue disk. And a few days later, he saw that that small blue disk had moved. At first, he thought it was a comet, just another wandering traveler shooting through our solar system. But with careful observation, he came to realize that he had actually discovered the seventh planet in our solar system. This was the first new planet found in recorded history. Herschel wasn't looking to make this discovery. He probably wasn't even the first person to have seen Uranus. He was just the first person to realize, as he hopped from known star to known nebula, that between all the known objects in the sky was a whole host of undiscovered faint fuzzy bits that needed mapped and needed reported and needed cataloged. And he did all those things. And these are just the discoveries we're most aware of. Herschel also discovered infrared light, thus the telescope being named after Herschel the person. And he was also a family man, which has led to some of the weirdest stories in astronomy. Between his music and astronomy, Herschel actually also found time to expatriate his sister when his parents died and bring her over to England where he was living. And Carolyn Herschel is perhaps unfairly, perhaps fairly, depending on how well you believe the stories, remembered as William's grouchy younger sister and also his constant assistant. Originally, astronomy wasn't her thing. When she moved from her family's estate in Hanover to join William in England, she originally gained notoriety as one of the most amazing soprano singers in the city of Bath. It was after her brother left music and began running most of his living through the building of telescopes that she became his assistant, because she could no longer sing in the symphony he was no longer conductor of. She went on to discover 8 comets, a number of nebulas, and it was while working with her brother that they recorded the locations of object after object after object in a catalog that would eventually go on to be that NGC catalog that all of us use even today. That NGC, that new general catalog, that dates all the way back to the work of the Herschels. She became the first woman to have ever received pay as a scientist when she was appointed as William's assistant, and she earned £50 a month. Even today, her 8 comets in a single lifetime is really an impressive achievement. And when we look back on history, when we look back at the Herschels, at Lord Rosse, at so many of the early people who contributed to astronomy because they had the personal wealth to build massive telescopes that academics just couldn't imagine affording. These amazing people were not everyday people. They were, in some ways, I'd guess, the Elon Musks and the Bezoses of their day, or at least the people wealthy enough to build personal observatories in their backyards. Citizen science, community science, really has become something of everyday people contributing to research. And that too is well lodged in history. in the modern era, it's thought the first citizen scientists were probably American colonists who recorded the weather. From John I can never say this poor human's name. From John Campanius Holmes' recording of storms in the mid-1600s to George Washington, Thomas Jefferson, and Benjamin Franklin tracking the weather during the founding of America. These men were united in a single purpose. They were trying to understand meteorology by recording enough data that when all their data, all the data of the people they inspired to help, was all put together, maybe some sort of a pattern, an understanding of when and where storms hit, could somehow be derived from all their measurements. It was Thomas Jefferson who first envisioned a network of weather observers. According to the National Weather Service, Jefferson recruited volunteer weather observers in 6 states, including Virginia, Massachusetts, Pennsylvania, Connecticut, New York, and North Carolina. It was on the foundations of this work that in 1849, the Smithsonian Institute set up a system for receiving weather data. By 1990, this still active today network had grown to 10,000 stations. You might have heard of this system today as the Cooperative Observer Program, and it's used by the National Weather Service with today well over 13,000 stations in the network. It is through the spread of technology that citizen science has been able to grow. And sometimes it's just everyday people that take our everyday technology and spread it to science. One of my favorite stories is that of Andrew Ansley Commons. He was a sanitation worker who photography was his hobby, and somehow he convinced his significant other to let him build a rather massive telescope in their yard. And he attached a new piece of technology, a glass plate camera, to this telescope. And he took the very first image of a sky object that we know about. And this, as is still true today for so many amateur and professional astronomers, his first image was of the Orion Nebula. And with this ability to start adding astrophotography to our arsenal of how we observe the sky, so many new things were possible. And this actually led to the formation of an organization many of you are probably aware of that originated right there in San Francisco. And this is the Astronomical Society of the Pacific. In late 1889, there was a solar eclipse that reached totality north of San Francisco. The local astronomy club, the local folks who did photography, all headed towards the center line, much the same way so many people headed towards the Ring of Fire eclipse last month. And for the very first time, folks had cameras. And they worked to record the solar corona. They worked to record what they saw using this new technology in a new way to study our sun. And when everyone got together in January at an informal meeting in San Francisco, the idea was raised that we need to partner your everyday person who has a camera, which admittedly was only upper middle class and wealthy at that point in time, and the scientists who didn't always have access to that equipment, together to work on studying the sky, on studying the sun, and so much more. The Astronomical Society of the Pacific was formed out of that meeting as a way that people could join together, collaborate together to study our sky. About the exact same time, we had the American Association of Variable Star Observers getting ready to start forming out of Harvard College Observatory. At this point, Pickering, who was director of the observatory, had laid out this notion that any moment that a telescope is used and not used for science is a moment wasted. And he called on every amateur who had a telescope to dedicate their efforts to doing science. And this idea of everyday people also takes a different form. This is that of people who change their own life by going from someone interested in the sky to someone taking on a second career in science. One of the most important stories I like to tell my Astronomy 101 students is that of, well, Milton Humison. Milton Humison dropped out of school and had no formal education past the age of 14. He worked as a mule cart driver as they were building Mount Wilson Observatory and went on to become a janitor at the observatory. All the while, he was peppering astronomers with questions. What is this thing that we're carrying up the mountain? Tell me what this observatory is going to do. Show me what you're doing with your telescopes. Humison was that person with all the questions. And in 1919, George Hale made Milton Humison a self-educated person who started his career as a mule cart driver, part of Mount Wilson's staff, and assigned him to Edwin Hubble as basically night assistant. Humison went on to discover comets. He performed the spectroscopic work on faint galaxies and supernova that allowed us to understand our universe is expanding and to see the origins of heavy metals in supernova remnants. In his lifetime, Humison measured the redshifts of more than 620 galaxies at a time when that had to be done one galaxy at a time, using glass plates that had to be exposed for hours and hours and hours. This is remarkable work. And over, we just kept seeing, as new technologies came out, everyday people said, and I shall use them for science. We saw Greta Reber basically innovate the field of radio astronomy in the early 20th century when he took his radio engineering skills that he had from commercial radio and used them to build, and again, I don't know how you get your spouse to agree to this. He built a 9-meter radio dish in his backyard and started mapping the sky. He submitted the catalog he created to the Astronomical Journal, which sent a PhD researcher to his house to confirm that what he had done was real. And his catalog is at the heart of so many radio catalogs that we use today. And the most important thing I can bring up here is each of these people who are making these contributions, these are people who took a technology, innovated a technology, and did not keep to themselves what they saw. David Levy was a hero to many amateur astronomers, and his passing makes the world a little less interesting. In his career, Levy discovered 22 comets, either independently or while working with Gene and Carolyn Shoemaker, and he discovered 41 asteroids. He was working with Gene and Carolyn Shoemaker when he discovered Shoemaker-Levy 9, which collided with Jupiter in 1994. Now, Levy got his roots as a kid at a private school with really bad asthma who really liked to observe and was told he could not go out and use his telescope unless he kept his asthma under control. So he learned to control his breathing so that he could go out and observe the sky. He has an English degree. He had an English degree. But he would go out and he would look up, and he had memorized so much of what's in the heavens that he could write down what he saw and record new objects. And he knew how to report that data so that the faint fuzzies he saw, the faint fuzzies that were new, could become new discoveries. And it's really this tradition of reporting things and building the habit of going out and looking up night over night that matters. We have Reverend Bob Evans, who discovered 42 supernovae from 1981 to 2009, at which point it became hard to keep track because he started working with so many digital detectors. And the thing was, those original 42 supernovae, those were all done by eye, looking at either the field of view on his eyepiece or images popping up on a screen. And because he had memorized so many galactic fields, 1,500 galaxies that he could consistently look at and go supernova, no supernova, research teams started bringing him in when they were observing and essentially using him the way we now use software so often to look at a field and look for changes. But he had a much better false positive rate. The human mind is still better than our software. And it is because there are so many amateurs out there that today, all the things that our massive professional astronomers focus in on can focus in on only the faint stuff and start ignoring the bright stuff. Let's face it, Jupiter is an object that is too bright for most professional ground-based telescopes unless you stick on half a gazillion, and I'm making up numbers, half a gazillion neutral density filters. It is a very bright object. But starting in 2009, we realized amateur astronomers now have such good telescopes, such good CCD or CMOS cameras, that things like monitoring for dark spots is now the purview of amateur astronomers. Anthony Wesley was one of the first people to do this. He literally, it was the standard story. He had a brand new telescope. He was taking an image of Jupiter, and lo and behold, dark spots. And what he saw, they did follow-up observations with the Hubble Space Telescope. How amazing is it to go outside, look up from your driveway, and have what you see lead to Hubble Space Telescope observations? I can only imagine this is one of the greatest inspirations that an amateur could have. And since then, we've seen Jim McKeon in 2016 see a bright spot. Jupiter is constantly getting clobbered by stuff. Everything I learned back in grad school about every 500 years for something like Shoemaker-Levy 9, totally wrong. And we know this because amateur astronomers, multitudes of them with their 14-inch telescopes, doing amazing things. They are also discovering spots on Neptune. They are the ones that when we look at Mars, one of the things we don't think about is up until recently, we didn't have a orbiter at Mars that was situated far enough out from the surface of the planet that it could see the entirety of the planet. Instruments like HiRISE will get you a few kilometers across, CTX, a few 100 kilometers across. And what you really need is to see the whole planet to find dust storms. And amateur astronomers can easily see the entire planet. And over, they're the ones who report, hey, dust storm starting up. And then, lo and behold, Hubble gets involved and we see, yes, dust storm took over world. And our solar system and the dots of light we see as stars aren't the only things being discovered anymore. we can, through microlensing, very, very rarely see gravity expand out the light we can see from a distant object. So background object, foreground object passes in front of it. Gravity of foreground object is able to bend light that was otherwise aimed at some other part of the universe towards us. And that bent light is extra. And so we see objects get brighter. And that increase in brightness allows us sometimes to find planets, because in a solar system where first a star passes in front of a background star and then its planet passes in front, we'll see two different magnifying events. Projects like OGLE that are focusing in on the center of our galaxy, and the Macho project, which is looking out at the Magellanic Clouds, partner with amateur astronomers to allow them to get better data than they can with their systems that are only in one place and only able to observe when it's nighttime. By partnering with amateurs, the entire sky can be seen at once, or one object can be followed hour after hour as our world rotates. And sometimes amateur researchers have skills and passions that research astronomers don't necessarily have the time or the mentoring to be able to learn. My favorite example is a gentleman by the name of Dr. Ted Strike. His doctorate in philosophy. He works at a small university. And on the left in this image, you see a not very good mosaicing of early Mariner images of Mercury. I saw these images in school books growing up. Many of you probably did too. On the right is the exact same data set, reprocessed in the modern era using Photoshop and basic FITS processing tools. And Ted got so good at doing this in his spare time that he very much confused his university's special projects office, because this philosophy prof is getting pulled in to a variety of NASA missions to process images to pull out data that we didn't know about. He was part of processing the Pluto and Charon images for the New Horizons team. He has reprocessed images from Viking to allow researchers to tease things out of the shadows that were lost in earlier attempts at processing the data. A few weeks ago, he processed the newest JunoCam data of Io. This is the year of Io for Juno, the mission orbiting Jupiter. Each orbit, it's getting a little bit closer as its orbit and Io's orbit begin to sync up. And at the end of the year, it will have the best image we've ever had of Io. But last month was pretty good. And it was Ted that was out there processing the data. And we're even seeing this with JWST. This is Judy Schmidt. Judy Schmidt basically checks like an addict of the best possible kind for new data to come down from JWST. And then she processes it sometimes faster than the mission can and releases what she does on Flickr, where researchers who study the nuances of what each color in these images mean, which reflect different chemistry, different temperatures, they can use her processing to fast track their own research. And we are seeing things with JWST that, well, here is a JWST image of a galaxy highlighting the cooler infrared heat, and here is a Hubble Space Telescope of the exact same system. JWST is truly piercing through the dust, and her image processing is bringing out details that, well, researchers that have so many other pressures on their time are still figuring out the nuances of doing in some cases. Now, this has still been a whole lot of individuals doing contributions, and it's amazing, and I love it, which is why I'm bringing it up. There are, for every Ted, for every Judy, dozens of other people out there ready to help with highly specialized skills. But there's also people who just want to help. And those are the people I personally work with in my research with CosmoQuest. My goal is to leave no technology unused for communicating science and doing science. And most recently, I took these technology skills that I like to use and turned them towards helping the OSIRIS-REx team explore a little asteroid called Bennu. About 10 years ago in 2013, I had a member of the OSIRIS-REx team that I knew through all sorts of different places reach out to me and say, look, we've got a problem. We're going to get all of our data from the mission back right before finals week. And our original plan was to use students to go through all the images and help us find a safe place to grab a sample from the surface of Bennu. But with all of our students heading off towards finals and then disappearing towards summer, this seems like a bad plan. Can you help? And I said, yeah. And so with OSIRIS-REx, my students got a chance to go see their first launch as we dreamed of getting to be part of this mission. And my students got one of the saddest and harshest reality checks because, well, we all traveled down to see the launch. We knew we wouldn't have the money to do the project unless the launch was successful. So all of us are down there watching the rocket launch going, I want to do the science. This is so cool. This is so amazing. While simultaneously knowing if something went wrong, it wasn't just a loss of science. It wasn't just a loss of possibility. It also meant we would all lose our jobs. And I'm here to say, I love working on spacecraft, but I don't think I ever want to get involved in spacecraft until after they have launched. Now, luckily, everything went well with OSIRIS-REx. A few days after launch, we were able to get back amazing images of the Earth and Moon to scale, separated by their actual separation. I love this image. It confuses so many people because they're like, wait, I thought they were closer. No, they are not. Now, once OSIRIS-REx launched, we knew we had to start writing software that would allow our volunteers on the internet to mark the locations of rocks, to mark the diameters of boulders, and to circle the locations of craters. These were all potential hazards. And the problem was we didn't have any images of Bennu that looked better than this. So we assumed that Bennu would look like Itokawa, a similar diameter object that had been previously observed and was seen to have a mix of things on its surface, rocks, boulders, fairly smooth areas, and a whole lot of areas that were extremely hazardous, like this one where you really shouldn't try and touch down with a spacecraft to grab a sample. But we also knew, for the most part, it wasn't that crazy of a surface. And so we wrote all of our software for mapping out Bennu, assuming images like this one, assuming that people would be able to go in and there'd be a few boulders, a bunch of rocks, but by a bunch, I mean a few dozen, not too bad. And maybe a handful of boulders, not bad. We ran estimates on how long it would take us to map the entirety of Bennu, based on it taking 2 to 3 minutes per image for people to map boulders, rocks, and craters on Itokawa. we figured it would take us a couple weeks. We'd be done well ahead of our 90-day schedule. It was good. It was good. And then on New Year's, we got to Bennu, and a whole bunch of us sat back and internally cursed very loudly because Bennu does not look like Itakawa. And my citizen science project got much harder. We had to resort to all manner of recruiting human beings to help us because our software continued to use the Itakawa beautiful, easy, totally possible to do in a couple of minutes images for its tutorials to train people how to annotate hazards on the surface of an asteroid. But about half of the people that went through the tutorial and got an actual image of Bennu, and this image, that's an actual image of Bennu. These images have hundreds of rocks, dozens of boulders, very few craters. And the craters just look like places where the rocks got smushed. Instead of taking 2 to 3 minutes per image, it was taking 20 minutes per image. Over the course of 92 days, it only took us 2 extra days. The research team did not think we were going to complete this project at all. Our humans were able to go through and map out 14 million hazards in all of the images they looked at. Now, we did have people look at a variety of images more than once to make sure that we could statistically compare results and everything played out. But let me just put this to you again. Over 92 days, less than 4,000 people, nearly 4,000 people, annotated 14 million rocks, boulders, and craters in images of the asteroid Bennu. We couldn't do this with machine learning because the amount of data we processed was still not enough to train a machine learning algorithm to make all these annotations. We were on our own, but we did it. And when our data was combined with the data from the mission team, it became possible for them to identify a crater. And as I said, craters are just areas where the rocks are mushed. It was possible to identify this crater, Nightingale Crater, as the site where Bennu would, it was planned, go in and gently touch the surface, grab a sample using what is best described as an angry vacuum cleaner, and bring that sample back to Earth. Now, the reality was Bennu is the consistency of a ball pit. And while it was planned that the arm would touch Bennu, grab the sample by sucking it up like an angry vacuum cleaner, and bounce away, and then fire its thrusters once it had gotten a reasonably safe distance from the surface. The reality is that the arm went about 30 centimeters into the ball pit of an asteroid. And it was the firing of the thrusters that freed our spacecraft. This asteroid is nothing like we expected. And that sample has recently made it safely back to Earth. It's now, some parts of it are starting to hit public display. There's one on display at the Smithsonian in DC, and research labs are starting to get their samples. And we now know there is organics, there is water, there is the stuff necessary to form life in the material of this asteroid that was mapped by nearly 4,000 people. And this really brings up the power of citizen science in our modern era. It is powerful to have hundreds of observers scattered around the world ready to point their telescopes up. It is powerful to have thousands of people on the planet ready to click into a website and annotate images. The scale and willingness of the public to participate in our science allows us to do things that we, in our scarcity as researchers, lack the number of students, the number of research dollars, and just the time to be able to accomplish on our own. And with they changed its name. With the LSST, which is a survey on the Vera Rubin Observatory, the large survey through space and time getting ready to start in 2024, we are about to experience a flood of data like we have never experienced. And it's hoped that the combination of machine learning software, citizen scientists looking at the things the machine learning doesn't understand, and follow-up observations by everything from JWST to ground-based observers is going to allow us to deal with that flood of data. But we already have floods of data from other things. SOHO, SDO, which I suspect are near and dear to the hearts of many of you out there watching in the COFFIES Seminar. These missions have been sending back data that is like the first stuff 4K televisions looked at was SDO data. I don't think a lot of people have fully internalized that. Prior to SDO, we were not getting back regular 4K images from anything. And then that little mission went up and it settled itself into its Lagrange point, and it started sending us back the kind of data that allows us to see nuances in the solar environment we have never been able to see before in resolutions we didn't have televisions for prior. It all came together at once. It all came together at once. And this has allowed videos to get processed by Zooniverse people in their Solar Stormwatch project back in the earlier 2000s. This is allowing projects today to engage students in going through images. And if any of you out there have an idea for projects that you need someone to just go through banks and banks of images, we have software to do it. And there are so many different ways to look at the sun and do science that aren't even all solar science. The SOHO mission in the 90s started sending back regular images of the area around the sun that are great for space weather. And we can actually start to see not just solar mass ejections, not just flares, not just Mercury growing a tail now and then. They also allow us to see comets that may never be seen again as they completely disrupt themselves getting too close to the sun. And what started as a hobby for many amateur astronomers eventually got codified by the US Naval Observatory and turned into a specific citizen science project to look for comets and measure them in SOHO data. And even though you might not think that it's still necessary, there are still amateur astronomers out there looking at the sun and reporting how many sunspots they see. This is because there's always the chance that our machine learning algorithms that count the sunspots in data are going to miss things. There's always a chance there's going to be a data blackout. Just in case something happens, citizen scientists are forming a backup count of what our sun is doing that continue a long record of human beings looking at the sun and tracking sunspots cycle after cycle, allowing us historically to discover things like the Mater minimum. It's all continuing. And I could just keep going. But right now, what I would like to do is say, you can be part of this. You out there who are watching and have your own ideas. With CosmoQuest, we have developed software that allows you to do more complex tasks than other citizen science programs are able to support. And the reason that we're able to do this is because we take the philosophy that we're going to treat and teach all of our citizen scientists the same way that I taught my students when I was a university professor. This all comes down to basically conversations I've had over the years with my collaborator, Fraser Kane. He has railed for almost 2 decades against the walls, the paywalls that are put up between citizen scientists and the journal articles that we produce using their data. He has railed against the fact that a student can get classes, can get one-on-one time with instructors, can show up to office hours, and a citizen science can't. And for the first many of those years that he railed, all I could say was, we don't have options that make it affordable. At the time, there weren't open source options for journal articles. At the time, there weren't free video streaming platforms. But back in 2011, that all changed with the launch of Google Hangouts. And since then, a variety of different platforms, Justin TV, Twitch.tv, YouTube Live, and the original Google Hangouts have all made it possible to live stream out content like is happening right now with this seminar. And this means that it's possible for scientists like me to teach hundreds of people at once live on the internet. I could conceivably go up to thousands, but I'm here to tell you, unless you are a SpaceX rocket, you are probably not going to attract thousands of people to your live stream. But there are people that will show up to learn because they want to. And when we partner this ability to teach through streaming platforms with the ability to map images, to annotate images using online platforms, it becomes possible for us to teach people about what's in the images and then invite them to map with us. And this is what we did with Bennu. Bennu images were terrible to mark. Everyone in my community now responds to the word Bennu with F Bennu, because at a certain point, when you are marking thousands and thousands of rocks, you hate rocks. But doing the science was so important that we struggled forward with what we were doing. And myself and my collaboration members, we would sit on Twitch. We would hate map Bennu. We were entirely honest about how we felt. And we would talk about what science we were allowing. The same way I remember sitting in an observatory with my advisor when I was taking observational astronomy, and there were the 10 of us in the dome learning how to operate the telescope. It was the same way I remember during an REU sitting in the dome and learning more about how to operate an even bigger telescope. Now we're doing this online. And this partnering of streaming media and online citizen science applications allows us to do more complex problems that allow more training than you can get just through a website. So if you have ideas, if you have things that you're thinking, I just wish I had students to help me. I just wish I could somehow afford to hire 20 students over the summer to go through this data, or 1,000 students. Well, reach out. CosmoQuest has thousands of people ready to do science who want to help you explore this universe that we share and together do remarkable things. All right. It is time to switch from the pre-planned portion of this presentation over to answering questions. And I am here to answer questions. I see one in the chat already. Let me move the chat up to where it's easier to see. Shea is doing an amazing job at, oh, I misplaced SDO. SDO isn't at the Lagrange point, it's geosynchronous. I totally misplaced SDO. Thank you for the correction. Wow, okay, I've said that many times and I've said that wrong many times. All right, let's see what else is in here. So Shay is saying, I could see doing something along the lines of tracking flux on the surface, similar to the AR spotter project, but with HMI. Okay, I am an astronomer by training. And I do not know either of those two abbreviations.
Sorry. I was commenting kind of to Coffee's cohort that are online, but
Okay.
but also, yeah, again, tracking magnetic flux on the solar surface. So there's one of the links that I posted in chat also is on tracking solar active regions with citizen science.
Yes.
And they're looking at it more in terms of the solar atmosphere. So using EUV images instead of magnetic images. But HMI is an instrument, the helioseismic and magnetic imager on SDO. And so looking at doing something similar with HMI and tracking the magnetic flux instead of just like the EUV active regions would maybe be an interesting project.
Yes, and we could totally put together something like that. I'm happy to collaborate. If I'd been smart, I would have put my email address on screen. I was not that smart, but I can type it into chat. So there's my email address. It's just plg@psi.edu. I hope I get points for super short email address. Other questions?
I have another question if nobody else does.
Go for it.
So a lot of what we are doing, I mean, so there's lots of things that we're doing in Coffees, but a good portion of it involves modeling and like trying to improve or create realistic models of the solar interior. Are there examples of sort of modeling efforts instead of just observational efforts that you can provide?
So modeling efforts have taken two different forms. There is the standard BOINC project that comes out of the University of California, Berkeley. BOINC is the software that was originally used for SETI at Home, which is not from the SETI Institute, and has gone on to be used for everything from Einstein at Home to there's a climate model that is based on it. And so what it's doing is it's using volunteered CPU cycles to run models that otherwise there's just not enough CPU cycles around to run. Now, the other side of it is there have been a variety of teams that have looked at sometimes what you need to do is match simulation data to actual data by sliding sliders up and down until they match. I'm destroying my microphone. This is something I remember doing as a graduate student working on high resolution stellar spectra, where it was okay, if I turn the carbon up and I turn down the technetium, can I eventually match everything? And this kind of model is actually something that's super easy to do with citizen science. The hard part is simply in making a user interface that a member of the public is willing to use, because it turns out that scientists don't really care about our user experience. This is why graduate students cry fairly regularly. So when you're developing software for the public, you do have to have a better user experience. But the other side of that is once you develop that better user experience for the public, there is nothing to stop professional researchers from using it. With our Bennu Mappers project, we actually had various versions of the project live so that the OSIRIS-REx team could have their own images in it that their internal team was doing follow-up data on, because it was a pleasant experience to map with Bennu Mappers. So yeah, it's all possible. It's all about creating the user experience that causes someone who's already said, yeah, it would be super cool to get to collaborate with researchers using mission data. That's a super low bar. To then look at the data and go, yeah, I can do this, and not run away for their lives. And people can run away either because the data is scary, Bennu, or because the interface is horrifying, which is most professional software.
I have a question.
Go ahead.
So this Bennu mapper, that's software that people download from your website and install on their personal computer.
It was done entirely through a website.
Oh.
So it was a combination of PHP and JavaScript. I get to talk tech. I am nothing if not a tech head, but most people know me as a science communicator. But the reality is I spend most of my time writing software. So the way it works is folks are each given the next image in the queue, where each image goes to order of 6 to 12 people, depending on how complicated the images are and how interested we are in getting additional statistical information. Basically, people will independently make mistakes unless there's something wrong with the software, but the right answer should be gotten at by more than one person. So by having multiple people all look at the same image, you know that things that are marked multiple times should be real. So the software goes through, distributes images, people annotate the images using just JavaScript libraries, and then they click submit, and it all gets stored in a MySQL database, and the research teams can download digests of all of the data on either a updated, what has been done since the last time they downloaded basis, or just download the entire darn thing. Now, we don't currently have any new citizen science projects up. We're in the process of working on one through a PDART for a planetary scientist who's doing some mosaicing work. And that should be going up in hopefully before the New Year's. We are in a good place to start new projects. Bennu is well behind us at this point. We like to put ourselves out of business by doing projects either completely in the case of Bennu mappers, or providing sufficient data that it's then possible to use our contributions to train machine learning algorithms. So these are our two goals: either complete the project or sufficiently train machine learning algorithms that we're no longer needed and can go out and do new research. Other questions?
Can I tell you about the germ of a crazy idea?
Yes, always.
So I'm a helioseismologist, which roughly means I study sound waves inside the sun.
Yeah,
And
yeah.
everybody here but you has heard this spiel before, but I'm glad to have someone new to tell it to. So usually you tell people you study sound waves inside the sun, like, oh, that's so awesome. What does it sound like? I'm like, oh, I never listened to it, and like a decade, that was my answer, and just felt like such a moron, and meanwhile I'm hearing on the radio people sonifying black hole data, and it was like,
yeah,
data doesn't even need to be sonified, it's already sound.
Yes.
So anyway, I've made a little bit of progress in this direction with the sonification of solar harmonics project. So I've made it where people can like download our time series and speed them up. Anyway, so the sun is a in just 30 seconds. The sun is a resonant cavity for really low frequency acoustic waves, a peak power at like 3 millihertz. So you got to basically speed it up by a factor of 100,000 to bring it up to the range of human hearing. Anyway,
Right.
all this data is freely available on the web. And so I wrote this software. So before I learned Python, these darn composers convinced me to write all this software in this visual programming language called Pure Data, which I went deep down the hole with this Pure Data. It's nice that it came with its own graphical interface, but anyway, I did, write all this code, and afterwards I learned Python, and now I'm going to have to redo the whole thing in Python eventually to potentially serve it on the web, hopefully. And but the thing is, so back to what you're talking about. So we've been looking at, graphs, plots of this data, for 50 years. And but we never listened to it. And so on the one hand, there's definite certain like pedagogical value to it. Like there's certain physical effects you can hear, like solar rotation and the large frequency separation that tells you about stuff in the solar core. But the thing is like we don't know actually what else could be audible in the data, because anyway, so one of my crazy ideas was to just start pumping this stuff out. Because so basically it's like usually we do 72-day time series. So that's like 100,000 in some points. And so you can usually play it, at the lowest audio rate in like 13 seconds, but that can also be changed. But for each 72 days, we generate something like 40,000 different time series.
Wow.
That sample different regions of the sun. And so that's how we use their frequencies to figure out like stuff like, sound speed inside the sun, because the different time series, sample different regions inside the sun. And that's why they have different frequencies, because the resonant cavities properties vary throughout the sun.
Yeah.
So I don't have any expectation of being able to discover anything by listening to the data, but it's something that I've been interested in letting people and putting out there. And I mean, just like, putting it out on even maybe just Spotify or something like that. And just, so that's where I'm at. And, but also to like, you could accompany like videos, like what the sun sounded like during a Carrington rotation. When you're looking at a 13-second video of 2 Carrington rotations, you could at the same time be listening to, basically synced up, the movie and the actual sound of the sun. So it's not really a question, just something I've been thinking about.
It's a comment, and that's okay. So this is the kind of thing where what I'd really want to do is partner the imagery, the graph, and the audio, and allow people to basically use their brains to do the multi-parametric solutions we all hate writing software to do. And have people be able to annotate when they hear something and see something, to look for the things that are visible and not seen, and the things that are seen and not heard. I'm using the wrong words. To find the things that are seen and not heard, and the things that are heard and not seen, and the things that are seen and heard.
Mm-hmm.
And that could potentially lead to something interesting. But it would need to be caveated with this is a fishing expedition and we don't know what we're going to find. But as long as you're fully honest the entire time, there is nothing wrong with fishing expeditions.
Mm-hmm. Yeah. And if the only thing it costs is my time, then
yeah. So reach out, let's follow up and see what's necessary to scope something out and see what's needed. And
really, would you be interested?
Yeah, I'm always interested.
Okay.
I just want to make science happen.
Nice. I'll email you right now.
Okay.
Mm-hmm.
I mentioned that this is also going out on Twitch, and one of the audience members over there is like, a listening light show, but can you dance to it? And I just need to share that.
Yeah. Can you?
I don't know.
Yeah,
We will
you
find
can.
out.
You can.
Go ahead, Shaya.
I have so many questions. But really my big one is Tim sort of touched on it, is funding. Is there funding support that needs to be provided to y'all to put this stuff into place? Like, how does that all work?
So I hadn't caught that in the chat. I've been rearranging my screen apparently too much. So if we're going to go fully live with something, we do try and find the funding necessary to do customization of our interface to match your needs and to make sure that the data delivery matches what you need. This is not a whole lot of money. We usually get order of $20,000. There is NASA seed funding through, I've completely forgot the name of the program. There is NASA seed funding through a program I cannot remember the name of, that I'm pretty sure the letters of intent are due now-ish. And it's a yearly call to basically do startup projects. And PDART funds this kind of stuff, and the National Science Foundation funds this kind of stuff. Now, the key with all of that is you really have to have clear scientific goals. The kind of fishing expedition thing is where CosmoQuest is funded through a variety of creative means. Getting research funds is very difficult. And I aided a congresswoman in a sexual harassment investigation in 2016, which did some bad things to my career. I do not recommend on a career level, although it was the right thing I did. So in order to keep a lot of our programs going, I went from 80% of my grants getting funded to 0% of my PI grants getting funded. Helping the congresswoman. We are now funded through a combination of advertising on our podcasts, Patreon from the general public, donations from the general public, and a variety of other squirrely means, like we're putting together a gift-giving guide of educational stuff for Christmas that will be coming out sometime this week. And as the director of CosmoQuest, I'm willing to use my discretionary funds to say, I think this is a cool idea. I have a student who isn't very expensive, who may be watching on Twitch right now. And let's go experiment. So, and I'm perfectly happy to help write grants with anyone. So this flexibility of, we're really good at being subawards, and we're really good at finding funding that doesn't require me to PI grants because I reported sexual harassment and do not recommend. It has allowed us to do things I never imagined we could do. Sorry for the TMI. It's a really weird story that led to very creative funding.
Unfortunately, that is the way of the world these days.
Yeah.
At least you're still here.
Yeah. Thanks to donors. So, okay. Other things.
Okay, it's about time. So if no other questions, let's thank our speaker today again. It's a wonderful talk and wonderful stories. I'm really interested by those interesting things that I'm not known before or didn't know clearly before. Thank you again. And same as before, the recording we will, after trimming, we will also put them online on COFFIES website. So those who probably could not attend today live could watch the recording. Okay, thanks to Pamela again, and so see you later at our future seminars. Thank you.